Assalamu alaikum students. So today we are going to discuss first law of thermodynamics and how we are going to use our Reynolds transport theorem to utilize this first law of thermodynamics and define the energy required for our system to run a system, or the energy that can be produced by a system. So what we are going to do is to derive the energy equation by using the Reynolds transport theorem and the first law of thermodynamics. So as you know, the first law of thermodynamics deals with the conservation of energy. And by conservation of energy, we mean that energy is neither created nor it is destroyed, but it is converted from one form into the other. If we would like to write equation, so the change in internal energy is equal to, means if any change in the internal energy of a system occurs, so that change is equal to the change in the heat content, that means the change in temperature of the system, plus minus the work done. Excuse me. That is the work that is done by the system, or the work done on the system. So it can be either plus or either it can be minus. We'll get back to the plus minus sign in a little while. So just to discuss the first law of thermodynamics, if any change in the internal energy of a system occurs, that change is equal to either the change in the heat content of the system, or either a work is done on the system or the work is done by the system. If a work is done on the system, it means let's say if we have a pump, that is a very common mechanical device, that is a water pump is used to pump water from low potential to high potential. So if we have pump, so we are working on the system. Remember that by system we mean our fluid. So pump is work on the system. So it means we are adding energy to our fluid. By system we means our fluid. So if we are adding energy to our fluid, that means that it is positive. So we will use a positive sign for that. If system does work on some mechanical device, for example turbine, in which from high potential we drop some water on the turbine and the turbine rotates. So the turbine rotates because that water has some energy due to its height. So that potential energy results in rotation of a turbine, and that is work by the system. So in turbine, the work is done by the system. It means the system loses energy in this case. So that is why we put negative sign for work by the system and work on the system, because the system, that is our fluid, the energy is added in this case, and the fluid loses the energy in this case, and that energy is again not created or destroyed, but it is transferred to some shaft, and that shaft in turn generates some generator, and it produces electricity, and in this case the electricity turns the pump, and that pump in turns add energy to the fluid to move it from low potential to high potential. So this is the work done on the system and work done by the system. Now let's move on to our Reynolds transport theorem, and let's see how are we going to utilize this conservation of energy phenomena in our Reynolds transport theorem, and how we can use our Reynolds transport theorem to determine how much energy we need or how much energy we can create. So first law of thermodynamics again deals with the conservation of energy, and we have wrote an equation for it and saw what different terms in that equation means. So how will we use this first law of thermodynamics in for our Reynolds transport theorem? We'll use it to determine how much energy is required to run a device, or how much energy can be extracted from a device. So By using Reynolds transport theorem and first law of thermodynamics, we can determine these two crucial elements, that is the energy required and energy that can be extracted from a device, a mechanical device. I gave you two examples, one of a pump. So the energy required to run a pump, or the energy in that case that can be extracted from water to run a turbine and generate electricity. So you can correlate those two examples. So again, just to be clear, if this is our system and the change in internal energy in that system occurs if we add heat to the system or we extract heat out of this system, or it can also the internal energy can also change if we work on the system or the system does work on some other mechanical device, and in that case it loses some energy. So these are the criteria in which the internal energy of a system change, that is due to the change in the heat content, that is the heat in and out, or the work done on the system or the work done by the system. So this is what results in change in the total internal energy of the system. So just to put it in equation form, and this is our left hand side of our Reynolds transport theorem, because you can see we are now talking about the total change with respect to time in the energy of a system. So that is the total energy of the system, and that total change with respect to time in the energy of the system will be equated to those two terms, that is the heat in minus heat out for the system plus the work done on the system or the work done by the system. We can write it in net change terms, that is the net change or the net heat in the system plus the net work done by the system or on the system. So this is what we can equate our left hand side of our Reynolds transport theorem to, that is this term, total change in the energy of the system will be this. This is again our left hand side of our Reynolds transport theorem. So now moving on forward, and we will see what our extensive properties will be, what our intensive properties will be. The extensive property in this case is obviously energy, but what are those energies and the different form of that energies, how will heat be added to the system, what type of work we are talking about. So we will talk about all these terms in the next slide. So let's move on. So now let's look at the extensive and intensive property of our Reynolds transport theorem. But before that, we want to explain this equation a little bit further. This is the total change in the energy of the system, and that is equal to this change, means the change in energy due to heat transfer. That is due to heat transfer, and that change in the system is due to work transfer. So by heat transfer and work transfer, we get our change in our internal energy, the total change with respect to time in the energy of a system by heat transfer and work transfer. Now let's look at the intensive and extensive properties. This is the extensive property, this is the intensive property. Our extensive property is our total energy, and our intensive property is our specific energy, that is total energy per unit mass. So these are my extensive or intensive property, but what will be this total energy equal to? Let's look at those terms. So my total energy will be equal to the internal energy of the system, and by system I mean fluid, plus the kinetic energy of the system and the potential energy of the system. So if I might write the right terms for these energies, so this is the internal energy of the system, this is the kinetic energy of the system, and this is the potential energy of my system, and these three energies comprises my total energy of the system. Now if I divide these terms by mass, so I get my intensive properties. These are my internal energy, my kinetic energy, and my potential energy per unit mass. So extensive property in this case is my total energy per unit mass, and this is what it is equal to. So now if we look at the generalized form of the Reynolds transport theorem, if you remember, this is how it looked like. That is, the total change in the extensive property of the system is equal to partial change inside the control volume plus the net flow into and out of this control volume through these controlled surfaces. So now let's look at our Reynolds transport theorem for our conservation of energy, and this is how it looks like. This is my total change dV over dt, and here instead of B I would like to write E. So that is the total change in the energy of the system is equal to this term, that is the total the change due to heat transfer plus due to work transfer. Now let's look at these terms, that is the change inside the control volume, partial change inside the control volume with respect to time. So that is the change in energy inside the control volume. This is the change in energy inside the control volume. But mainly we will be focusing on steady state flow problems. So in that scenario, we will equate this to 0, because we've already discussed that steady state in steady state flow the properties do not change with respect to time. So any term that represents change with respect to time, it will be equated to 0, and this is this term, the partial change with respect to time, that is representing the change in energy inside the control volume. So we will be dealing with steady state flow problems, so we will equate this term to 0. Now let's look at this term. This term represents our net flow of energy in and out of our control volume through these control surfaces. So that is the net rate of flow of energy. This term is the net rate of flow of energy. So this is what these terms mean now. So now let's look at the heat in term and the net work that is added to the system or extracted from the system. So what will this work be equal to? What will this heat be equal to? We have looked at the intensive properties and extensive properties of the system in this slide, and we have come to know that the extensive property is the total energy, and that total energy is equal to these terms, and my intensive property is the specific energy, and that specific energy will be equal to these terms. But now I want to know what will be the net heat in term equal to, and the work rate term will be equal to in this Reynolds transport theorem. So now let's look at this. Now let's see the right hand side of this equation, that is the net rate of heat transfer, that is the net rate of heat transfer and the net rate of work transfer. Heat transfer occurs due to change in temperature, means the net change in the total energy of the system can occur by adding heat to the system or by extracting heat from the system. So that occurs due to change in temperature. But what about work transfer? How will the net change in energy occur due to work transfer? So let's look at work transfer, rate of work transfer, and rate of work transfer is equal to, that is the net rate of work transfer required to increase or decrease the total energy of the system. So that net rate of work transfer is equal to the rate of work transfer to the shaft plus the rate of work transfer required to overcome the normal stresses plus the rate of work transfer required to overcome the shear stresses. We will come back to these normal and shear stresses in a while, because you will now be wondering what are those normal and shear stresses doing here, because we are only talking about work and heat. So let's get back to them in a little while. We will first discuss this rate of work transfer for the shaft. So the work transfer for the shaft is equal to the work done on the shaft, that is work done by the shaft, sorry, if the work is done by the shaft. And in this case, the best example is the pump, because in pump the work is done by the shaft on the fluid. The work is done on the shaft by the shaft on the fluid. So in that case, energy is added to the fluid. So that's why we have put a plus sign here. You might not see it, but here is a positive sign, because the energy is added to the fluid in this case. And the other can be the work transfer from the fluid to the shaft. So if the fluid is working on the shaft, that is in case of turbine, because in turbine, you know, we have already discussed that the fluid does work on the turbine rotates and generates electricity. So that is the work done by the fluid. So in this case, the fluid is losing energy, and when it is losing energy, we will represent this with a negative sign. So that is the rate of work transfer due to work done on the shaft or work done by the shaft. And now we will look at the terms. These are the rate of work transfer required to overcome these normal stresses and these shear stresses. And when we are talking about the rate of work transfer required to overcome these stresses, we are talking about the control surfaces of our control volume. And by control surfaces, I mean the inlets and outlets of my control volume. So this is what first I'm going to discuss the rate of work transfer required to overcome the normal stresses. So this is the rate of work transfer, and this can be written as force into velocity, the force required to overcome the normal stresses into velocity. Sorry, this is not volume, this is velocity. So I can also write it like this, that is F dot S over T, and Fs over T gives us the rate of doing work, and this is also equal to power. So if I'm talking about the rate of work transfer, I'm in general terms talking about power, not explicitly work, because I'm again and again repeating this word, rate of work transfer. So we are actually talking about the power transfer here. So the rate of work transfer required to overcome these normal stresses on the control surfaces is equal to the force generated due to these normal the force that will generate these normal stresses into the velocity. Now what does this mean? How does these normal stresses occur on our control surfaces? So let's look at an example, and in an example we have a pipe and we have control surface. So this is the control surface of that pipe, and this is control surface out. So here the fluid is coming out. When the fluid is coming out, it will encounter a pressure, an outside pressure. This is an outside pressure. An outside pressure will be exerted on this control surface. On this control surface, an outside pressure will be exerted. So in reaction to that pressure, an internal stress will be generated. So that is what we call a normal stress, that is generated due to this external pressure. And this external pressure is acting on this control surface. So due to this external force, that is pressure in this scenario, an internal stress, that is the normal stress, will generate on this control surface, and to overcome this internal stress, we will need to do some work. So that is the work required to overcome these normal stresses. So now let's simplify these terms more and write it in terms of stresses and pressure. So this is what we are going to get for the work required to overcome these normal stresses will be equal to stress n unit vector and delta area dot V, and I can represent the area, I can represent the area by n unit vector. You have already known this term that is used to give a directional sense to the area, because this is the controlled surface through which the fluid is going out. So the normal for this area will be drawn like this, and this is a unit vector normal whose magnitude is 1, only showing us the direction of our control surface. This is the stress, because I can write it in terms of, if stress is equal to force per unit area, then force is equal to stress into delta area. So this is how I wrote it. Dot V is the velocity, and I can also write from the scenario that I have developed to explain this normal stress. You can see that if this is our normal stress occurring due to this external pressure, so you can see that the stress and pressure are both in opposite direction. So I can write that my normal stress is equal to negative of my pressure. So I will put negative P in terms of stress here. So now I get negative P n unit vector delta area dot V, and to simplify it a bit further, I get minus P, P is for pressure, V is for velocity, dot n unit vector delta A. So this is the work that is required to overcome these normal stresses that are occurring on this control surface. And why are they occurring on that control surface? This is due to this external pressure. So to overcome this external pressure, certain amount of work needs to be done on these control surfaces to overcome this external pressure, and ultimately for the fluid to come out of this control surfaces. And the only way the fluid is going to come out of this control surfaces is that it overcomes this external pressure. So by overcoming this external pressure, we are talking about doing this amount of work too. So apart from rate of work transfer to the shaft, we are also talking about the work required to overcome these normal stresses on the control surfaces. Again, I am talking again and again about the control surfaces, because this work will only be required on the control surfaces, because the normal stresses will only occur on the control surfaces. Plus the work required to overcome the shear stresses. These are the shear stresses. They also occur on our control surfaces, and they are due to the viscous effects. The viscous effects that occur inside our fluid. The effects due to viscosity. And by viscous effects, I mean the effects that we used to discuss, that if a fluid is flowing like this in this direction, it will have a certain velocity profile, and this is the velocity profile of this fluid. You remember this, that why the velocity profile is like this? Because due to the no slip condition here, the no slip condition near the boundaries of this pipe. So due to the no slip condition, our velocity profile will look like this. So these are the viscous effects. So a certain amount of work also be required to overcome these viscous effects. But what we do is we assume that our flow is inviscid. And by inviscid, I means that there is no viscosity. And by assuming this, the work required to overcome these shear forces will be equated to 0. So far I have made two assumptions for deriving the energy equation by using the Reynolds transport theorem. One is that my flow will be steady, so this term will be equated to 0. And then in the rate of work transfer, the work required to overcome these shear forces, this term will be equated to 0. So what I am going to put now, instead of the rate of work transfer, the net work in, that is this term, I will put these two terms. that is the rate of work transfer to the shaft or by the shaft, and the rate of work transfer required to overcome the normal stresses on the control surface. So now let's put these two terms here and write a Reynolds transport theorem for our energy conservation. So let's move on. So now this is how our Reynolds transport theorem will look like. If we go through these terms again, on the right hand side you can see that we have the net rate of heat transfer, and we have already discussed that that rate of heat transfer is due to delta T, the change in temperature. And then we had a term for the net rate of work transfer, and now in the previous slide we have equated that work transfer to the rate of work transfer to the shaft and the net rate of work that is required to overcome the normal stresses on the control surfaces. And this negative sign is due to this equation that we wrote, that stress is equal to minus P for that particular scenario. So this is why this minus sign is here. So now we have a control surface integral on the right hand side and a control surface integral on the left hand side. So what we will do, we will move this term to the left and see what happens. So what we will get if we say that this is a steady state flow problem, which we will assume throughout our calculations. So this is the control surface integral of intensive property density V dot NdA plus the integral for the control surface and rate of work transfer required to overcome the normal stresses occurring on the control surface. So this is the pressure, velocity, and the unit vector normal representing the direction of the area and differential of this area. So what we can do is we can write a single integral for both of these terms. So writing a single integral for these terms, we will get our intensive property, density, velocity, and unit vector normal representing the direction of the area plus pressure, velocity, dot, and unit vector normal and differential area. So as you can see, we can simplify this more by taking some terms common. So if we take density, velocity, and dA common, we will be having an integral that is E plus pressure over density, and the term that is common out is density, velocity, dot, and unit vector and dA. So this is what we have done to simplify our integral for the control surface further, and by taking this term common, that is density, velocity, dot, product of unit vector n and differential area A. By taking the density common, we have taken the density common from this term, and by taking common from this term, by taking the density common from this term, what we have done is that we have divided the pressure by density. So this is how we have got these two terms, that is the specific energy, that is our intensive property, plus pressure over density. So now we can also write this. If we write the terms for our intensive property, that is our specific energy, so that is the specific internal energy plus V square by 2 specific kinetic energy plus GH plus P over rho. So this is what this term will look like, and this term will be multiplied with as such, that is rho V dot N dA. So this is what my control surface integral will look like now in this Reynolds transport theorem by making some simplified assumptions and putting in some values. So just to clarify that how we will end up with this equation is, so at the end this is our energy equation that we get by using the first law of thermodynamics and by using our extensive property as energy in the Reynolds transport theorem. So we get this equation, and just to clarify that how we got this equation, so this is the term for the control surfaces that we just wrote. So just to be clear that how we got these terms on inside the control surface integral, now you know because we've solved it. And on the right hand side we get the rate of heat transfer plus the rate of work done on the shaft. So this overall is known as the energy equation, and we have derived this. And again, in our assumptions, if our flow is steady, this term will be 0, and if our flow is adiabatic, this term will also be equal to 0. That is for adiabatic condition. And in adiabatic condition, if you remember from your thermodynamics course, adiabatic condition is that condition in which neither heat is going into the system or out of the system. So in that scenario, our rate of heat transfer will be equal to 0. Plus, if we are looking at a scenario in which there are no moving parts, then the rate of work transfer to the shaft will be equated to 0. So from time and time again we will look at our situation, the problem statement, and we will see that what the scenario is. So if it is adiabatic, then our rate of heat transfer will be 0, and if we are looking at a problem where there are no moving parts involved, so then our rate of work transfer to the shaft will be equated to 0. But that these conditions that we are applying now depend on the problem that we will be solving. But this term, that is the partial change with respect to time and the flow of energy inside the control volume with respect to time, will be equated to 0 because we are dealing with steady state flow problems throughout. So that's what we're going to do in the near future, that we will be dealing with steady state problems, and this term will be equated to 0. So this is the energy equation that we will be left with, and again these two terms can also be equated to 0. This is for adiabatic condition, this will be equal to 0, and this term will be 0 when our problem scenario involves no moving parts. So then this term will be equated to 0. So now let's simplify this energy equation a little bit more and write and apply it to a scenario, a simple scenario in which a fluid is going in and out of a simple pipe, and write equations for control surfaces and see how we can simplify this energy equation and write it in terms of enthalpy. So let's do this. Now let's apply this equation to a simple flow, a simple pipe flow. As we have a stream tube here through which a fluid is going in. So we have one control surface here, and here the fluid is going out. So what we are going to do is we are going to write equations for these control surfaces by using this control surface integral in our new energy equation. So again this will be equated to 0, and now let's write some equations for these two control surfaces. So this is what we are going to get if we apply this control surface integral on these two control surfaces, that is control surface for inflow and that is the control surface for outflow. So we will get these two terms and also multiply by the mass flow rate, and this is what this term is equal to. rho VA, that is equal to m dot. So if we write it for this stream tube, then we'll get these two terms for our flow out and our flow in, or as we can say for the energy that is going out of the control surface and the energy going inside in the control surface. So this is how our energy equation will look like. Now if we write it in terms of net flow, that is net flow of internal energy, the net flow of pressure, the net flow of velocity, and the net potential energy. So this is equated to the rate of heat transfer plus the rate of work transfer on the shaft. So we can simplify it a further bit more by combining these terms, that is the specific enthalpy here. This is called enthalpy, and enthalpy is the total heat content of the system, and that is equal to internal energy plus pressure over density. So enthalpy is also equal to total heat content of the system is equal to internal energy plus pressure into volume. If we want to see how this term is equal to pressure into volume, so that is pressure into volume. So I can write this pressure and density mass per unit volume. Density is mass per unit volume. So if we take this to the numerator, so we get pressure into volume divided by mass. So what we are talking about is a specific enthalpy, because we are defining it for per unit mass. So this is our specific enthalpy. So combining all these terms, the internal energy and the pressure over density terms, and writing this equation in terms of enthalpy. So this is how we can write our energy equation in terms of enthalpy as well. That is the net enthalpy, that is the net velocity, and that is the net potential energy, and that is overall equal to the net rate of heat transfer and the net rate of work transfer to the shaft. So this is what our final form of energy equation, if we want to write it in terms of enthalpies, will look like. And sometimes we will like to write our energy equation in terms of enthalpies to apply it on particular scenarios that we will see in the coming example. So this is our energy equation, and as you can see, our energy equation was derived by using the first law of thermodynamics and the Reynolds transport theorem, and by taking the extensive properties as our energy and equating it to the change in energy, we got our energy equation in terms of our generalized equation, that is our generalized energy equation, and in terms of enthalpies as well. So this is our energy equation, and now we are going to use it to see how much energy we can extract from a device, or how much energy a device needs so that we can run it. So this is our energy equation, and now we are going to use it to solve our problems related to energy. So let's do that. Now look at this example. In this example, we are required to determine the horsepower required by the pump. So here we are calculating the horsepower by using our energy equation. So let's read the statement. The pump delivers water at a steady rate of 300 gallons per minute. So this is our volumetric flow rate as shown in figure 5.20. This is our figure just upstream of the pump. This is the upstream. This is the upstream of the pump. Section 1. This is our section 1. This is our inlet of the pump. This is our section 1 and inlet of the pump, where the pipe diameter is 3.5 inches. This is the pipe diameter of 3.5 inches. The pressure is 18 pound per square inch. Pressure at section 1 is 18 pound per square inch. just downstream of the pump, section 2, where the pipe diameter is 1 inch, the pressure is 60 psi, pound per square inch. So this is our section 2 where the fluid is getting out. So this is the pressure, 60 pound per square inch, and the diameter in inches. The change in water elevation across the pump is 0. So we will, this is interesting because we will, in our control surface integral, we have terms for potential energy. So in this case, the height is 0, so those terms will be equated to 0. Let's get back to them in a little bit. The rise in internal energy of water U2 minus U1 as associated with temperature rise across the pump is 93 feet into pound per pound mass. So this is the rise in internal energy U2 minus U1. The pumping process is considered adiabatic. So the rate of heat transfer, the change in internal energy due to rate of heat transfer will be considered 0 because the process is adiabatic, as we discussed in the previous slide that what those conditions can be, and one of those conditions was adiabatic condition. So that rate of heat transfer term will be equated to 0 in our energy equation now. So let's look at our equation now. The flow is a steady state, and as we discussed, we will only discuss steady state flow problems. So that partial or partial T term for our control volume is already equated to 0 in this equation. So don't get confused that our equation has changed somehow. This is our change in internal energy that is given as this value, that 93 foot-pound per pound mass, and this is our elevation, and as they said that the change in water elevation across the pump is 0. So this term Z2 minus Z1 will be equated to 0 because there is no transfer of energy due to change in height. So these terms in the controlled surface integral will be equated to 0, and now the pump process is considered adiabatic, so the net rate of heat transfer is also equated to 0 due to adiabatic flow. So this is what our energy equation will look like now. So let's move on to the rest of the solution, and what we need to find is this power. This is the rate of work done by the shaft on the fluid, and this is the horsepower that is required of us to find. So what we don't know in this equation is the mass flow rate, but we can calculate that mass flow rate from the volumetric flow rate. We know these two terms. We know the pressure at outlet, the pressure at inlet. We don't know these two velocities, V2 and V1. We can find that with the help of our conservation principle, that if we consider that m dot 1 is equal to m dot 2 is equal to m dot, so we will be able to find these two velocities, and this term is also equated to 0. So we will find these unknowns, convert them into their proper units, and then put it in this equation to solve it for horsepower. So let's do this. So now let's find our unknowns and put it in our energy equation to find the horsepower that is required for this particular pump. So first of all, we will find our mass flow rate. So that mass flow rate is equal to density into volumetric flow rate. So density of water in this particular case is 1.94 slug per cubic feet, and this is the volumetric flow rate, that is 300 gallons per minute. So these terms, that 32.174 pound mass per slug, is used to convert this slug into pound mass, because we need to convert these terms into appropriate units, and this 300 gallons per minute is converted into cubic feet per second. So for that purpose, we will divide it with this term, 7.48 gallons per cubic feet, and for seconds we will divide it by 60 seconds per minute. So these terms, this term is used to convert this into pound mass, and these two terms are used to convert the volumetric flow rate into cubic feet per second. So we get our m dot, our mass flow rate, as 41.8 pound mass per second. Also, we need to find the velocities, and for velocities we will use our volumetric flow rate equation, and from that we will compute our velocities by putting in appropriate values for the area at section 1 for velocity v1. And again, these conversions are done again and again in each step. You don't need to do them again and again, you just need to do them in the start and just put the values in the equation. So area here is pi d square by 4, so in this case this will be d1. This is d1. It is in inches, so it needs to be converted into feet, so that's why this term is here in the equation. And this is the 300 gallons per minute, that is again the volumetric flow rate. So to convert it into cubic feet, this term is used per second, this term is used. So overall we get our velocities as v1 is equal to 10 feet per second. For velocity v2, the same procedure is done by putting in area v2 and here d2, that is our 1 inch. So that inch is converted into feet and gallons per minute is converted into cubic feet per second. So we get our velocity at point 2 is equal to 123 foot per second. So now we have known our unknowns, that was our mass flow rate, our velocity at point 1 section 1 and our velocity at section 2. So putting it in the final equation that we got after cancelling out the q term, because this was a adiabatic process, we will now solve it for our power, and we multiply it with this m dot. This is the mass flow rate. This is the change in the internal energy, U2 minus U1. This is P1 over density term. Here again, these terms are for unit conversion. And this is for P2 over density terms. Again, these are for unit conversion. Plus, this is my velocities. These are my V2 minus V1. And these are again for unit conversion. Multiply by this term. This term is used because these terms inside this red bracket will give me power in terms of foot-pound per second. But to convert it into horsepower, I will multiply it with this term as a whole. So I will get my work rate, that is my power, in terms of horsepower, and that will be equal to 32.2 horsepower. So if you see the comment section, there is very interesting comment that of the total 32.2 horsepower, internal energy changes accounts for 7.09 horsepower. The pressure rise accounts for 7.37 horsepower, and the kinetic energy increase accounts for 17.8 horsepower. So the beauty of this energy equation is that of the total horsepower, we can see that out of this 32.2 horsepower, how much is going to the rise in the internal energy, how much is going to the rise in the pressure, how much is going to the rise in the kinetic energy. So we can disintegrate this total power into the terms that is contributing to, that is the increase in the internal energy, how much is going into the internal energy, how much is going into the pressure rise, and how much is going into the kinetic energy rise. So this was our first example from your Munson book. Hope this was clear.